Right, good morning, everyone. Welcome back from spring break. So we're halfway through the semester, and we sort of haven't heard anything different from our leadership. So kind of the plan is to keep going online until we're told otherwise. So this is kind of the format that the class is going to be in from now on until further notice. So we're just gonna plunge in and do it, okay? So let me see if there's any questions before we start, but the plan is to do a lecture on sections 3.9 and 4.1 today. And on section 4.2 and sort of start a new chapter on number theory. It's R4.1 because it's I'm using materials from a different book. So that's the plan for this week. And these will be via Zoom. They'll be recorded, so you guys can refer to it later. And due dates for this week, quiz 7 is due by Wednesday night, and the writing assignment 4 is due by Friday night. Okay. All right. So, any questions before we start on the lessons? Check my chat. All right. Okay, so let's get started then. Okay, so we're looking at section 3.9, which is the last section, chapter 3. This is a big chapter on proofs, right? Okay, so let me get to, all right, let me share the lecture screen. There we go. Okay, so now that we sort of went through some of the formal proof process and sort of the kind of logic law that shows how sort of proofs work, okay, and sort of connected with the truth tables that we've learned. Now we're going to apply some of these proofs to some mathematical statements. Okay, so let me answer a couple of questions. So is the lecture going to be on Zoom instead of putting on Canvas? So the examples in the lecture videos are in Canvas already. So if you notice, there are lectures for section 3.9 and 4.1 and 4.2. And I'll probably keep putting them. But I guess I checked the YouTube views, and very few people actually pre-watch the lectures. So I recognize that a lot. If I'm kind of coming to class expecting that you guys have pre-watched them, then I guess my expectations are unrealistic. So I suspect a couple of you probably watched it, but most of you haven't watched the lecture videos before class. So I'm going to basically just lecture during the Zoom session, so you guys get the information. I will try to leave time for questions. So if you're working on the quiz and you have questions on the quiz, I'm happy to answer them towards the end of the class and also during office hours. Yeah, so I think I'm just going to lecture during the Zoom session because I'm kind of finding it that I'm not getting enough views on YouTube ahead of the lesson time, that I can actually assume that students are pre-watching the lecture videos. Second question, how can you know what you missed on test 2? Okay. So I graded the test in Canvas. Okay, so I guess I don't want to pull up anybody's test because I don't want to reveal grades right now, but I want you guys to check. Okay, so if you open up your test submission, you should be able to open your files. So whether you send me a PDF file or whether you send me JPEGs, you should be able to open those pictures and they would have like red markings on them. So check marks and comments and crosses and the points that I've taken off. So hopefully I'm not the only one that sees them. So they should be marked up. They should be revised with my notes on it so you can see what you got incorrect, right? So please let me know if you can't see them, and I'll see if I can figure out a way of how to get that feedback to you. Hopefully you can see them because it took me probably 4 times as long to grade the test in this format as it does on paper. So if I don't have to do any more work on it, I would be really happy. All right. So, okay. So Andy said that if you click on view feedback, you should be able to see my comments. Thank you for that. Okay. All right. Suki, what's the plan for project 1? Okay, so I think I mentioned that last time. So I'm going to merge the 2 projects into just 1 project. So there will be only 1 project during the semester. It will be due at the end of the semester. So instead of it being a group, 2 group projects, it will be 1 individual project. I will give you some information on that later. Plenty of time to complete it. And so I'm hoping it's going to be about the same amount of work. Okay, so no more project 1. That's not on the schedule anymore. Okay, please check out the revised schedule and revised syllabus. Those are in Canvas. And you can kind of see what the pacing will be. I'm sort of trying to make up for that last week. Okay. So does it mean I'm going to stop uploading the lectures on YouTube? No, I'm not going to stop. I'm still going to make those because I think they are very I think they're very helpful. I notice people watch them because I look at the YouTube hits, like how many people watch them. They were watched during the test, which is fine. They have a great purpose. So as you guys are working through the quizzes or you're working through the test, they're being watched. So I think that they're helpful being in sort of the 15-20 minute sort of chunks rather than the whole Zoom session. So I'm still gonna keep making them. I think they're a good resource and they're gonna be a really great resource next time I teach discrete math. So my purpose is to keep making those videos, okay? But during our time together, I will basically just lecture using the same example. So if you pre-watch them, that's fine. It will kind of reinforce it. And if you didn't pre-watch them, that's okay too. All right. Okay. All right. So I don't see any more questions for now, but again, feel free to keep asking. And I'll answer them. If I'm in the middle of sort of lecturing and doing examples, I probably won't answer right away if it's not related, but I'll definitely answer your questions toward the end of the class. Okay, so let's do it. Section 3.9. So we're going to look at using proof methods to prove more mathematical statements. So far with the laws of logic, they were fairly abstract. They were just like, you have S&P and Q and R, and you have all these kind of premises, and with the conclusion, you could use like direct and indirect proof, or sort of things like, Maria is a computer science major and stuff like that. So, but now we're kind of basically how do we actually use these concepts to prove some math things, okay? And you'll see these kind of proofs for the rest of the course now, when we kind of go into set theory, going back to set theory and going back to number theory. There'll be proofs coming up fairly often. I'm muting people. Make sure when you come in that you mute yourself unless you have a question for me. If I hear background stuff, I'm going to mute you. All right, so we're going to have sort of mathy theorems that we're going to see from now on that we'll prove occasionally for the stuff that we're going to be doing. All theorems in math can be expressed in either the form premises, therefore conclusion. So that's an implication format. All right. Or the equivalence theorems, which is the if and only if. Okay. So if we have some statements C1 and you have some statements C2, the double arrows means equivalence. So those are if and only if theorems. And for those, you need to do 2 steps. You need to prove them both directions. Okay. If C1, then C2, and if C2, then C1. It's not enough to just go one way. All right, let's see. Okay, so let's start with the implication proofs. Okay, so there are 2 basic ways of doing the proofs, direct proof and indirect proof, which is by contradiction. But there are other ways that we'll go over. Okay, so let me pick a better color. So in example 1, it says give a direct proof of the theorem. If n is an odd integer, then n squared is odd. Okay, so we're going to do this with direct proof. Okay, so that means that we start with our premises. So this is given, and you take that to be true. Okay, so if n is an odd integer, so n is odd. Right, so there's a particular way to express that something is odd mathematically. If n is odd, we say that n can be written as 2k plus 1, where k is any integer. Okay, so that's how we express odd numbers mathematically. All right, so this is our premise. This is taken to be true, and now we need to see if we can prove the conclusion. Okay, so taking this as true, how do we figure out if n squared is odd? Okay, most of the time we plug stuff in. Okay, so we're going to plug in. All right, so we need to figure out things about n squared. So we're going to plug in this truth statement into n squared. And we're going to get 2k plus 1 squared. Okay. And we work this out, we do a bit of algebra, and we get 4k squared plus 4k plus 1. And we need to convince ourselves that this is an odd number. Okay, so let's try to write in a format. So this is, if I factor out, let me factor out a 2, we get 2k plus 2k squared plus 2, then plus 1 plus 2k. Sorry, I'm losing k's. All right. So I factor out a 2 here from the first 2 terms, then I have that plus 1. And the reason I did that is because I wanted to look like an odd number. Okay. So is this 2 times an integer plus 1? And yes, because this is an integer. If k is an integer, then 2k squared plus 2k is going to be an integer. So because this is an integer, 2 times an integer plus 1 is going to be an odd number, right? And that's the end of the proof. That's our direct proof right here. By starting with a premise that's true, we assume this is true, and we basically plug that into the part of our conclusion there and demonstrate that that's also true, that that's an odd number. All right, any questions with that problem? Okay. All right, so I'm experimenting with my Zoom. I saved the screen. Okay, let's see, I'm gonna clear this. Go to the next one. Okay, so yeah, we'll do a few of these problems. We'll keep with these proofs. They're with us from now on, amongst other things. It's not all proofs from now on. Let's see. Where's my draw? Okay, there it is. Give a direct proof. If m and n are both perfect squares, then nm is also a perfect square. So again, here's my premise. And then I'm trying to prove this conclusion, okay? So we look at, says m and n are perfect squares, okay? So we kind of try to write that property mathematically, right? So if m is a perfect square, then I can write it as an integer squared. If n is a perfect square, then I can write it as an integer squared. So k and l are both integers, right? So we kind of use the facts that they give us to express that mathematically. And then we look at our conclusion. So we are trying to show NM. Okay, so we're trying to prove something about the product NM. So we plug in. We're going to plug in for M and for N in here. So replace N by L squared. Replace M by K squared. All right. And by the property of numbers, by the property of exponents, we know that we can write these as L times K squared, right? And because K and L are both integers, this is going to be an integer. So I ended up with the product N times M is some integer squared. So therefore, this is a perfect square. Okay. Any questions with that one? And that's it. That's the end of it. Okay. All right. I'm going to go to the next one now. So let's clear this one. Okay. Now with an indirect proof. Okay. So we're going to go through an indirect proof. So just like we've done indirect proofs before, right? So you assume that the conclusion is false, and then you try to come up with some sort of contradiction. Okay, so indirect proofs are very useful in cases where direct proofs are not so nice to do. Okay, so I'm going to do this with an indirect proof first to show how it works, and then I'll attempt to do a direct proof in this one and kind of show that it's basically a direct proof is a bit nasty, okay, or not even possible. All right, so indirect proof means that we're going to negate the conclusion. All right, so we have our premises, and we're going to negate the conclusion and see that that leads us to a contradiction. Okay, so if n is an integer and n squared plus 2 is odd, so these are my premises here, right? And this is my conclusion. Okay, so my premises says that 3n plus 2 is odd. And when I negate the conclusion, that tells me that it's not true that n is odd. Okay, so it's not true that n is odd means that n is even. Yeah, so how do I write that? So n is even, I can write as n equals 2 times k, where k is some integer. Okay, so with the indirect proof, we work backwards. We kind of start with this negation of the conclusion, and we're going to plug this into our premise and see what happens. So what we're hoping happens is some sort of obvious contradiction. And then once we get the contradiction, we say, hey, well, yeah, the conclusion could not have been false. Okay, so let's plug into 3n plus 2. So I'm going to plug in there. So we're going to say 3, and n is 2k plus 2. Once again, this comes from here. And when I simplify, I get 6k plus 2. And I notice that I can factor a 2 from there. And what I'm getting is that the 3n plus 2 number turns into 2 times something that's an integer, but that's the definition of an even number. Okay, so I started with the premise saying it's odd, but I came by plugging in, I saw that that has to be even. So this is our contradiction here. So this makes the contradiction. Right. So by sort of what those laws of logic, we basically can say that if there's a contradiction, that means that our assumption that the conclusion is false is incorrect. So that means that C has to be true. C is true. So N has to be odd. All right. There you go. So that's how an indirect proof works. Okay. Any questions with that? All right. So let me look at this again, but try to use a direct proof. Okay, so I'm kind of trying to convince people that indirect proofs are great. Sometimes they are. It sort of depends on the situation. Okay, so let me look at this problem again down here, and let's try to use a direct proof. So if I do a direct proof. Okay, so direct proof says, again, you start with your premises, and you try to see if the conclusion is true. Okay, so we start with saying that 3n plus 2 is odd. Okay, so if 3n plus 2 is odd, then I can write it as 2k plus 1, where k is an integer. Oops, k is an integer. All right, and then we need to figure something about n. We need to figure out that n is odd. Okay, so I can try to solve this equation for n. So I'd say 3n is going to be 2k minus 1. Divide everything by 3. And we get n equals 2/3 k minus 1/3. So this is what I get to. All right. Now, can I say that this is odd? So I get this equation right here, like n equals 2/3 k minus 1/3. I can't really conclude that this is an odd number. I know like k is an integer, but if I look at some values of k, if k equals to 1, then I get 2/3 minus 1/3, which is 1/3. This is not an odd number. This is a fraction. If I look at k is 2, I get 4/3 minus 1/3. And that gives me 3/3, which is 1, which is an odd number. Okay. So it works for some values of k, but not for other values of k. So you're it's not convincing that n is an odd number for all integers. So this is like a direct proof. You get somewhere, but it's not conclusive. Okay, it's kind of, well, it works in some cases, but not some other cases. So an indirect proof, it's a much better approach here because not that many steps and you come to a definite conclusion. So I think you can sort of work with the direct proof here to maybe separate things into cases and kind of see when it works and when it doesn't, but it's a bit more unsure of what you're doing with the direct proof. All right. Any questions with that one? Okay. All right, so I'm going to clear it and go on to the next example. Let's see what the next example is. Okay, let's clear the screen. Okay, so this is another indirect proof one. All right. So if n equals ab, where a and b are positive integers, so I'm looking at a number which is a product of two positive integers, then a has to be less than or equal to square root of n, or b has to be less than or equal to square root of n. All right? So here are my premises. And this is my conclusion. And I want an indirect proof, okay? Which means that I'm going to take my premises as true and negate the conclusion and arrive at a contradiction. All right, so let's negate the conclusion. Okay, so if I'm negating the conclusion, that means I'm saying it's not true that a is less than or equal to square root of n, or that b is less than or equal to square root of n. All right, so notice that this is an or. Okay, so it's an or right here, disjunction. So I'm negating this disjunction. When I distribute the negation, it's going to be, it's not true that a is less than or equal to square root of n, and it's not true that b is less than or equal to square root of n. Okay, so De Morgan's law, right? So let's see, if it's not true that a is less than or equal to square root of n, then a has to be bigger, strictly bigger than square root of n, and for this part, b has to be bigger than square root of n, right? So notice we're kind of using those laws of logic on these mathy statements to change the sort of negation of a disjunction with De Morgan's law, and we turn it into a conjunction. Okay, so this is the negation of what my conclusion boils down to this. Okay, so now let's plug this into the premise. So let's plug this into n equals ab and get to a contradiction. All right. So if I plug this into here, if n equals ab, and if a is bigger than square root of n, then that means that n is going to be bigger than square root of n. And if b is bigger than square root of n, we plug in like this, okay? So I'm plugging in square root of n for a and b, but because a and b are bigger than the square root of n's, then you end up with n being bigger than square root of n times square root of n. Okay, so when you simplify this, that means n is bigger than square root of n squared. So n is bigger than itself. Okay, so here's my contradiction. Contradiction. All right, so that's it. That's the indirect proof. We started with negating the conclusion. We plugged it into our premise, and we came with the contradiction. Okay, so the contradiction basically says, well, the negation of our conclusion must have been wrong. So that means our conclusion is correct. So the conclusion is true, which means that a has to be less than or equals to square root of n, or b has to be less than or equal to square root of n. All right. Any questions with that? Okay. Let's save this. All right. Are we ready for example 5? Show that square root of 2 is irrational. Okay, I'm gonna clear it and scroll up. There we go. Oh, I think that's the last example in the section. All right. So give an indirect proof that square root of 2 is irrational. Okay, so this is our conclusion. Okay, notice that we don't really have any premises. I guess we do have certain premises, and those premises are about what we know about rational and irrational numbers. So even there's no like explicit premises in here, we have prior knowledge about numbers that will sort of be used as premises. Okay, so the indirect proof says that we're going to negate the conclusion. Negating the conclusion says that we're going to assume that square root of 2 is actually rational. All right, so let's see what that means. So a rational number means that I can write the number as a fraction, as it means that I can write the number as a reduced fraction. So rational means that I can write the number as a reduced fraction. Okay, so that's kind of the definition of a rational number. Okay, so that means I can write it as a over b. Okay, so a over b are integers. And I also need to put a condition that b is not equal to 0. So that fraction exists and makes sense. Okay. All right. And this part is important, that this fraction that I wrote here is reduced. So that means that a and b have no common factors. Okay. So I can't like divide both numerator and denominator by the same thing. Okay. So reduced fraction means that a and b have no common factors. All right. Okay, so we're going to start the proof now. Okay, so we're going to get rid of the square root. So we're going to square both sides. Okay, so let's square both sides of the equation. So square this side and square this side. And then I get 2 equals a squared over b squared. All right, so I'm going to multiply both sides by b squared. And we get 2b squared equals a squared. All right, so what I got to here is that a squared is 2b squared. So a squared is 2 times an integer, right? That means that a squared is an even number. Right? Now, if a squared is an even number, then a has to be an even number, an even integer. Okay, now I am making the statement right here without proof. Okay, so it's like I'm saying a squared is an even number, therefore a has to be an even number. Now that might make common sense by intuition, but I'm going to prove these in a few minutes. Okay, this is actually called a corollary. Okay, if you have a theorem and you're proving it, and somewhere along the way you're sort of making this statement that might not be clear, or it's like, where'd you come up with that? It's like, is that really a thing? Then what you might have to do is kind of go, well, I'll prove this beforehand, or I'll prove it after, but it might be sort of something that you need to prove along the way. as part of proving another theorem. But let's kind of finish the one with the square root of 2 is irrational, and I'm going to prove this in about 2 minutes. Okay. All right. So I'm saying that if a squared is an even number, then a has to be an even number. Okay. All right. Now, if a is an even number, I can write a as 2 times an integer. I can write a as 2 times k, where k is an integer. All right, so let's plug this into here. Okay, so I'm going to plug it into there. So I'm going to have 2b squared equals 2k squared. So that's going to equal 4k squared. Divide both sides by 2. So I'm going to have b squared equals 2k squared. All right, so this is a statement about b squared. So now b squared is 2 times an integer. So I can conclude from here that b squared is an even number. And from here, I can conclude that b is even. All right, so I got that a is even, and I got that b is even. So here I showed that a is even, and here I showed that b is even. Okay, this is my contradiction. Right, so this contradicts what I started with at the beginning. Okay, so I said that if square root of 2 is rational, it can be written as a fraction of a over b, where a over b is a reduced fraction that have no factors in common. But if a is even and b is even, they do have factors in common. They're both divisible by 2. All right, so this is a contradiction right here. Right? So that contradiction leads us to the conclusion that square root of 2 has to be irrational. All right, let's see. Okay, I shouldn't write at the very bottom of the screen. All right, are there other indirect proofs that square root of 2 is irrational? I guess this is the only, that this is like the standard historical one. I haven't seen any other proofs. Of course, there's often this is a fairly famous historical proof. And for things like this, people do try to come up with other ways of showing it. But this is sort of the standard way of showing the square root of 2 is irrational. Just kind of showing that both the a and b have to be even. Any other questions with this one? All right, so let me take this. Okay, so I'm going to take this statement right here that I made. All right, if a squared is an even number, then a has to be an even number. Okay, so I'm going to go up here and prove that. Okay, so I use that as part of my theorem, but let's convince ourselves that that's actually true. Okay, I think that might even be, I'm not sure if it's a problem on the homework, but it's definitely problems for kind of the practice in the book. Okay, so let's prove that if a squared is even, then a is an even number. Okay, so I'm going to do it with an indirect proof. I like indirect proofs. Okay, so basically we're going to assume that it's false that a is even, which means that a is odd, which means that I can write a as 2k plus 1. And if I plug this into the a squared, then this is going to be 4k squared plus 4k plus 1, right? And factor out a 2, we get 2k squared plus 2k plus 1. And this is an odd number because it's 2 times an integer. So this has, we concluded that a squared is odd. Okay, so assuming that a is odd, we prove a squared is odd. So this is a contradiction. So it means that a has to be even. Okay, so this is an aside. This is called a corollary to this sort of theorem we're trying to prove down here. If there's sort of any parts that we kind of have to jump from one thing to another that we sort of don't already know, then you can sort of prove it on the side. All right, any questions of that one? Okay. So these are the examples in section 3.9. Okay. I feel like, let me just check something. I feel like I put more examples, but they're not in that particular file. So let me just, give me a second. Let me check my folder. Section 3.9. No, wrong folder. Oh yeah, okay. I did. I adjusted it and put more stuff on it. I think that was an old file. So let me pull up some more. Here we go. I have more examples here. Okay, cool. Yeah, that felt like not enough. Okay, so here's a few more. All right, so good. Example 6 is the if and only if proof. Okay, so this is one of the equivalence ones. Okay. All right. So this says if n is an integer, then n is odd if and only if n squared is odd. Okay. So this one we have to prove two ways. We have to go forwards and backwards. Okay, so we're going to look at the first part of the proof, part 1. You have to show that if n is odd, then n squared is odd. And the second part of the proof, we have to show that if n squared is odd, then n is odd. Okay, and you have to do both. All right, so I want to let you guys take a couple of minutes to try both of these. Okay, so again, with these two-part proof with if and only if, you can use like you can use direct proof for both of them, or indirect proof for both, or direct proof for one, indirect proof for the other. So you can kind of use a combination. All right. So yes, while you do that, I will upload the fresh file into Canvas because I think that one's missing a few problems. So go ahead and take a couple of minutes to try these out, and I'll upload the new file right now. Oops, sorry about that. All right. Okay, so that's done. I put the new file on there. Okay, so let's look at these examples. You guys had a couple of minutes to look at it while I was doing that. So these are very similar to some of the ones that we've done with the even and odd. I think this first part is pretty much like the first example, right? So this one is good with direct proof. Okay, so if n is odd, then n squared is odd. So n is odd means that I can write n as 2k plus 1. And then we plug into n squared. We get 2k plus 1 squared, expand it out. 4k squared plus 4k plus 1. Then we factor out a 2 to get it to look like an odd number. And it does, because this is 2 times an integer. This is an integer right here. You can even rename it something else. So it's an odd number. Okay, so that first part is solved. Going from n is odd to n squared is odd. All right, now going backwards, this is better with indirect proof. You can do direct proof, but there's sort of more like hand waving and sort of more writing involved. Indirect proof. So we're basically assuming that it's not true that n is odd, which means n is even. So I can write n as 2k, where k is an integer. And we plug that into n squared. So n squared is going to be 2k squared, which is 4k squared. And I can rewrite like this, 2 times an integer. And I can see that this is even. Okay, but that's a contradiction because we knew n squared was odd. So the contradiction says that negating the conclusion was actually not a good thing to do. Well, it was good, but it's not correct. So that means it proves the conclusion true, which means that n is odd. Okay, so again, it's sort of this is like, if you intuitively, you know this is true, but these are great examples to use when we're sort of with this proof methods, because it kind of let students kind of get used to the sort of more formal process of showing things. So yeah, that's a good point. The sort of, they're worded differently, but the approach is the same. So yeah, the approach is very similar to these problems, that you basically, you taking one part of the theorem and you plug it into the other. All right. So so yeah, for the direct proof, you're starting with n is an odd number, you plug it into n squared, and you're showing that n squared is odd. So direct proof, you're starting with something true, and you're proving that what you wanted to be true is actually true. Okay. With this part right here, with the indirect proof, you're assuming that conclusion is false, something about n, but you're still plugging into n squared. But we're showing that n squared is actually false, all right, which you don't want. So it must have been that your assumption that n was incorrect. So n is odd. But yeah, you're basically doing the same thing, taking the n and plug it into n squared. So if you can sort of do things so the simpler expression gets plugged into the more complicated ones, then it's sort of an easier process than taking the more complicated expression and simplifying it to the simpler ones, because that's when it can get a bit ambiguous. Right. Okay. Any questions with that one? Okay, so let's look at the next example. All right, so let's talk about a couple of proofs, vacuous proofs and trivial proofs. And both of these are typically found as part of bigger theorems. Like you're going to prove a theorem that you have to look at sort of separate cases, then you will see vacuous and trivial proofs as part of the bigger proof. And a perfect example is the trivial proofs you've already seen as part of an induction proof. When you look at the basis case, like P at 0, at P at 1, that part of the induction proof is a trivial proof. Okay? But let's look at what they are. So vacuous proof is, you can prove that a conditional statement, if P then Q, is true when we know that P is false. Right? Because if P then Q must be true and P is false. Okay, so if you know your premises are false, then by default, this implication is true. And that comes from the definition of implication, right? If you remember the truth table for an implication, right? P's and Q's, you have your choices: true, true, false, false, true, false, true, false. Then the implication, you have 1, 0, 1, 1. Okay, so we're here, right? So for the vacuous case, if you know your premises are false, then the implication is automatically true. Okay, so for example, if it says show that the proposition P0 is true, where Pn is, if n is bigger than 1, then n squared is bigger than n, right? So if I look at P0, this is the case when n equals to 0, right? So if I plug in n0 in here, then that says if 0 is bigger than 1, then 0 squared is bigger than 0. So because this part is false right here, this implication is true by default. So it's proven by default. Okay, so it doesn't mean that this part is true. It doesn't mean that 0 is bigger than 0. Right? This does not like imply this. Yeah, it doesn't mean that this part of it is true or this part of it is true. It means that the implication is true. Okay, so this is the vacuous proofs where the premises are false to start with. Then you haven't like broken your promise. So the implication is true. All right. So the trivial proofs are when, again, you're looking at a conditional statement, but you know the Q is true. So you know the conclusion is true. Okay, so this is the cases in the truth table here and here. So you already know that the conclusion is true. Then you can see from the truth table that the implication PQ is automatically true. Okay, so it kind of doesn't depend what the premise is. If you know the conclusion is true, it is true. You don't have anything to do. Okay, so again, these come up in induction proofs. So let's say if A and B are positive integers with A is bigger than B, then A squared is bigger than N squared. The universe is all non-negative integers. Show that P0 is true. So P0 is when I plug in N is 0. And basically, if I have A is bigger than or equal to B, then A0 is bigger than or equal to B0, right? When I simplify this, I get if A is bigger than or equal to B, then 1 is bigger than or equal to 1, okay? So this is the Q, this is the conclusion, and we can see that it's true. So this is like a trivial proof. The conclusion is true automatically, regardless of what the premise is, right? So again, I mentioned these because they're not like sort of standalone proofs. They're part of proofs where you look at different cases as like a induction proof, like we've seen induction proofs where you have to consider the P equals 0 case. All right. So let's look at a couple more things. So counterexamples or proof by cases. Okay, so a couple more proof methods. So these are sort of alternatives to like the direct and indirect proof. And so counterexample is that if we have a statement like every x px, okay, so, or for all x px, this means that for all x, that statement p of x is true. To show that such a statement is false, you need only find one counterexample. So one example of x for which that mathematical statement is false to disprove the whole statement. So in example 9, show that the statement every positive integer is the sum of the squares of two integers is false. So this is a statement of this type. So for every x, p of x, where p of x stands for the statement that every positive integer can be written as the sum of squares of two integers. So n squared plus m squared. Okay. So we're going to find the counterexample. Okay, so one example that shows that this is false is enough to show that this universal statement right here is false. All right, so giving me an example of a positive integer that is not a sum of two squares. Anyone? 5, 6, right? 6 can be written as 2 plus 4 or 1 plus 5 or 3 plus 3, right? And that's it, right? Can I use 0? I think we're looking at positive integers. Okay, so these are, obviously, I cannot write 6 as the sum of two perfect squares. So this is a counterexample. So I can't write 6 as a sum of two squares. Right. So this means that that universal statement is false. Okay, so that's a proof by counterexample. Okay, and now let's look at proof by cases. Okay, so proof by cases, example 10. Says proof that if n is an integer, then n squared is bigger than or equal to n. So a lot of things kind of lend themselves to proof by cases. Sometimes you have to consider odd and even numbers. Sometimes you have to consider positive or negative numbers. It kind of depends on the situation. And you usually kind of note that it has to be by cases when you're starting a proof. You can start like proof with indirect or direct proof and kind of go, oh, wait a minute, these cases are different than these ones. So you start separating things. So in this one, I'm trying to prove that n squared is bigger than n. It kind of lends itself to, oh, I have to look at negative and positive numbers. I'll maybe take 0 as a special case too, because different things happen with positive or negative numbers. So let's look at case 1. Let's say that n is 0. Okay, so if I look at n is 0, 0 squared is bigger than or equal to 0, and that's true. Okay, then we're going to look at case 2, where n is a negative integer. Right, so if n is a negative integer, n squared is bigger than n, and that's true because n squared is always positive. Actually, not the equal sign. So n squared is always positive because I'm squaring something, and n is negative, and a positive number is always bigger than a negative. So it's true in that case. Right, for case 3, let's look at n is a positive. All right, and let's see if this is true. Okay, so is n squared always bigger than n? When n is a positive integer. Okay, and you can see that's also true. Okay, so basically for integers, right, if I started 1 squared is going to be bigger than or equal to 1, and then 2 squared is bigger than or equal to 2, 3 squared bigger than or equal to 3. And again, you can do this by induction, right? So it's sort of, you can see the pattern, but as I kind of mentioned before with mathematicians, like patterns, do they keep continuing? So for case 3, you can say, well, I can do this by induction to make sure. All right. So by induction, I already have my basis case here. I could sort of, or I can say my basis case is P1. And that says 1 squared is bigger than 1, which is true. And then my inductive case, we're going to say PK is true. And PK plus 1 is k squared, k plus 1 squared has to be bigger than or equal to k plus 1. All right, so we can take this and add 1 to both sides. All right. Okay, and then if I also added 2k to this, sorry, add 1 to both sides. So I can also say that k squared plus 2k plus 1 is bigger than k squared plus 1. So if I add this extra term because k is bigger than 1, this is going to be bigger than that, right? Which is bigger than k plus 1. And then if I square it, if I factor it, then I proved that the inductive step is true. So you can show case 3 by induction if you want to sort of be really formal with it. All right, so that was proof by cases. So kind of looking at things that lend themselves to separating things into positive, negative integers. Again, sometimes you see things with, let's look at odd integers and even integers and other things that sort of make sense that it's different cases will act differently. All right, any questions with this? Okay, so I'm going to look at the next section. Okay, so let me stop sharing for a sec, just make sure that, let's see. That's not it. Yeah, so that's the end of chapter 9. And the next thing on the agenda, let's see, here's the announcements. All right, yeah, we're gonna look at section 4.1, okay? As I said, I adjusted the schedule. So if you go to Canvas and click on schedule and also sort of the revised syllabus, you can see a couple of changes, but basically just to make up for that last week, with the last week over there, I shuffled some sections around, okay? All right, so let's look at, we're kind of, chapter 4 has a couple of sections in it. It kind of goes back to set theory, and you can see how set theory applies some of the how proofs connect with sets. Okay, and yes, quiz 7 is due on this Wednesday, and I think it covers up to section 4.1. Okay, so let me go over that section. Barely. We have about 15 minutes left. Okay, if I can find it anytime now. There we go. Actually, that's not it. I have too many things open. Okay, yeah, there's quiz 7. It's on sections 3, 8, 3, 9, and 4, 1. Okay. And yeah, I think I need to go back to Canvas to open up that section. And of course, I don't think I'm almost there. 4.1. All right, let me share my screen again. There we go. Okay, so proofs for sets are main ways to prove things with sets are first, like counterexamples, just sort of like the last example that I did, not the one by cases, but the previous one, that you come up with an example that contradicts something you're trying to prove that it's false. Then we can prove things with Venn diagrams. That gives us a like very visual way of doing things. Membership tables, which are like truth tables, and by definitions, okay, which is sort of the most useful method of proofs, but also kind of the longest one. So we'll see how that works. Right. So let me show a couple of examples here. All right. So by counterexamples, I want to prove that the complement of the intersection of two sets is not the intersection of the complements of the two sets. Right. So by counterexample, you basically can come up with some sets. Let's say A is set 1, 2, 3, and B is set 2, 3, 7. And let's say the universal set is 0 through 9. Right? So first, let's do this side. So intersection of A and B is going to be the elements 2 and 3. But then when I take the complement of the intersection, that's all the elements in the universe that are not 2 and 3. So this is going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay. So now we're going to do the other side of the expression. So we find the complement of A, which is everything in U that's not in A. So 0, 4, 5, 6, 7, 8, and 9. And we're going to find the complement of B. So everything not 2, 3, and 7. So 0, 1, 4, 5, 6, 8, and 9. And then we find the intersection of these complements. So what's common between these two? And we see that it's 0 and 4 and 5 and 6 and 8 and 9. Okay? And when we compare the two, they are not the same. Okay, so this kind of one example, one counterexample showed that inequality, the equality doesn't hold true. Okay, so counterexample, really good to prove that something is false, and not a good method for proving an equality. So if you're trying to prove that two things are equal to each other, you can't prove that by just giving one examples, because when you're proving that two things are equal, you're trying to show that they're equal for all the universe, and one example is not sufficient for that. So you have to do it in general terms. All right, so all these other methods are kind of for that. We're going to try to prove equalities, so we can't just give one example or even two examples. We have to show them in general. All right, so let's look at proving with Venn diagrams. Okay, so using Venn, you draw a picture for each part. Okay, so for this part right here, we're going to take a universe and we're going to draw two general sets. So kind of the most general is that the sets do overlap. Okay, so we want to find the intersection of these two sets first. All right, so let's look at the intersection, which is here. Okay, so this here represents the intersection of A and B, right? And then draw another picture to show what you want. We want the complement of the intersection of A and B. All right, so we want the complement of the picture above. So the complement is going to be everything in U that's not in the green region right there. All right, so I want everything outside this here. All right, and the bigger brush. There you go, we get the point here. All right, so this right here is intersection of A and B complement. Okay, now let's do this other side. Okay, so we're going to do the other side of the equality. Again, here's my universe. And I want to find the complement of A. And I want to find the complement of B. It should be B. And then the union between these two. Okay? So the complement of A is everything in the universe outside. Let's see. I'm going to draw. Okay, this is a bad idea. Oh, that's thicker. Oh, okay, that's better. There we go. The complement of A is everything outside set A. Okay. And the complement of B is going to be everything outside set B. So let's do this here. There's A and B. And we're going to do the complement of B. So it's everything outside set B. Okay. And then the result has to be the union of these two sets. Okay, so if you kind of take these two drawings and take the union between these two drawings, the union is everything in the red and the green. All right? So if I kind of put them on top of each other, I see that the shading is right there. Okay. Okay. And now we compare the two. We can see that the drawing for this side and the drawing for these sides are identical. It represents the same set. So that's a proof. That's a visual proof that these two sets are actually equal to each other. All right. Okay, so let's look at proof using membership tables. Okay, so membership tables, we're basically using a truth table to show that both sides are equivalent to each other. Okay, let me do, I want to do one with subtraction. I don't have one. Okay, yeah, let me actually do example 6 with membership tables. I like this one better. All right, so I want to prove that A minus C intersect with C minus B is the null set, okay? So in a membership table, it's like having propositions. So I see I have 3 sets. So I'm going to have 3 columns to start with. And again, you put in your typical 1s and 0s. Okay. So what the 1s and 0s mean here is 1 means that an element is in the set, and 0 means that an element is not in the set. All right, so if you kind of think of, let's take X to be a random element, okay? So having a 1 here, that means that that element is in set A. And a 1 here means that element is also in set B, that element is in set C. So the 1s and 0s kind of tells you whether an arbitrary element is in set A or set B or set C, okay? So now we're going to make a column for A minus C. So subtraction of sets means that an element is in A, but not in C. So the way that an element is going to be in the difference between A and C is if you have a 1 in the A column, but a 0 in the C column. Okay, so if I compare the 1 and the 1, that's not going to be in the difference because it's in both sets. If I look at the 1 and the 0, that is in the difference because it's in A, but it's not in C. Okay, 1 and a 1 gives you a 0. 1 and a 0 gives you a 1. Okay, so the only way that you get a 1 in the difference is if you have a 1 in A and a 0 in C. It is in A, but not in C. Okay, so these are all zeros as a result. Because 0 means it's not in A, but it's in C. Okay, so that means it's not going to be in the difference. All right, now let's do the difference between C and B. All right, so again, to be in the difference, it has to be in C, but not in B. So the only way you get a 1 for the difference is if you have a 1 in C and a 0 in B. So that happens here, and that happens here, but then the rest are zeros. So these are zeros, these are zeros, like this. Okay. Now we do A minus C intersect with C minus B. And intersect means the same as a and, as a conjunction. So the only way that it can be in this intersection if it's in both. Right, so it's not in either of these. It's in the first one, not in the second, so it's not going to be in the intersection. So the only way you can get a 1 is if it's in both sets. Okay, so we get a column of zeros. So that means this is equal to the null set. All right, so that means that it's like there are no elements in A minus C intersect with C minus B. Okay, so that's the null set right there. Cool. All right, so I haven't quite finished 4.1. All right, so as you're working through the quiz, I made the quiz be due on Wednesday night. Okay, so I still sort of will take time in class on Wednesday to go over some examples in this section. But again, you can also watch the videos. Let me share my full screen actually. You can also watch the videos that I posted in Canvas for those. Let's see, where is my website? Over here, there we go. So I'll record, as I said, I'm recording this session. I'm going to post it in this tab right here. And quiz 7 is here. Okay, I think that's the end of the lesson. If you guys have questions, please hang around. I'll be around for office hours for a while. So make sure that you ask me any questions that you have. Okay, all right. That's it. Bye, guys. See you Wednesday.
Good morning, Professor. I had a couple of questions if you had time.
Yeah, sure.
I'll type the first one because it's pretty easy. It's just an understanding, but here, I'll type it. I have it saved here. So basically, does that negation apply to the one right in front of it or the whole quantifier set? Like if there's two quantifiers?
It applies to the whole quantifier set. It kind of, it moves from left to right. Okay, so So let me see if I can write that.
What's that second one then?
All right, so if you have this, so if you have for every x there exists a y such that some statement, right? Okay, so yeah, first it moves through the universal and it turns it into an existential. Sorry, it's backwards. Then it moves through the existential and it turns it to your universal, and then it goes in front of the proposition, in front of the statement.
Okay, I'm just making sure that that's how that property works.
Yeah.
Am I allowed to screen share?
Yes, of course.
Also, another question here. You cannot start a screen share while the other is. Okay, I have to.
I'll stop sharing.
Thank you.
There you go.
Thank you. Let me know if we're good.
Yeah.
Okay, let me fix this here. So, what's the best way to approach after I? Come on, stop. Gosh, there we go. My thought process. Okay, so 4 here. I understand how to read these.
Okay.
When you're choosing one, so when they come in a particular order. So I just hope my thought process is correct on this one, but I'll start with the for every, because this is the one I feel most confident about. So this one, for every x, there is a y that will make this true.
Yeah.
Basically, you just have to find, to prove it false or true, you just have to, so what did I do here? Oh yeah, I just picked a random one that made it false.
Yeah, so a counterexample, you can just pick a specific number that shows that that's false.
I guess this one then that I was confused about. So this one I solved for the element itself. So I solved for x and then found out where like wouldn't be a y. Like it says every y, and then this isn't every y, because if y was 1.
Right. So
I don't know if that makes sense to me.
So B says there exists an x. So for every y, P of xy is true. Okay.
Right.
All right. So you solved for x. All right. And you showed that. So basically, this says that there exists an x value. So it doesn't matter what you plug in, that will always equal that x value. So it's not just that y is not defined at 1. It's not true, because I can't have like a specific value of x where this fraction is true no matter what value of y you plug in.
Okay. So
does that make sense?
So then how do I solve for that then? Do I just have to find examples of it, or is there a way? Because I thought mathematically like this, it would make sense.
You have to say that in words.
Okay.
Right? So it's like there is no specific x value that will always equal to that fraction regardless of what the y value is. So yeah, you have to explain it in words.
Okay, no problem. And then last one for this one. Does this right here just turn into B? That's where my primary question came from, because this turns this into existential,
yeah,
which is right here, and then it negates this negation.
So yeah, that absolutely turns into B.
Okay, that was cool. Thank you.
Yeah.
And then my very last, and I'll get out of your hair. Starting to lose it on Charlie here on C. For any 2 real numbers, prove that x and y absolute value is less than or equal to x plus
Okay.
y. So where'd I start? I haven't looked at this since the other day. We're on the same page here. So I said, if x and y are above 0, so they're positive, x plus y, this would be 0. This would be 0 because they equal.
Yeah.
0. And then conversely for the individual, 0 plus 0, so these equal each other in that.
So for that case, for the case when there's 0, we're good. Okay.
Now, I guess where I get weird is when it's below and it doesn't equal 0. I don't know if I'm defining this right. So I said there should be a plus in there, but actually maybe y. Oops, shoot. Man, I don't know how to software anymore.
Yeah, PDFs are weird. PDF editor is not nice.
X plus y, but this would be negative x minus y.
Exactly.
Okay, so I have this. So all I have to do is prove that this one would equal this one, which it will. Yeah, which it will.
So you're considering the cases when x and y are both negative.
Yes, and then I'm going to try the inverse.
And x and y are and where they're backwards, opposite. All right, who's making it? Yeah, you're sounding pretty loud there.
I'm seeing. Do I still sound?
Yeah.
What the?
Unmuting myself. How about now?
Wow. So you have the right approach there. Yeah, you just have to look at the cases when they're both negative, when they're both positive, when one is negative, one is positive.
Okay.
And show that it works in each case.
Okay, case wise is exactly right. Okay.
Yeah.
Well, other than that, thank you. Stay not sick.
You too. Okay, bye. See you Wednesday. All right, so let me pull up the quiz. Okay. Here's the quiz. So you want number 5. Okay, so let me read through this. I haven't looked at the quiz in a while. So what do the following propositions say where U is the power set of 1 through 9? Which of these propositions are true? Okay, so U is the power set. So this is the set A right here. U is the power set of the set A, which is the elements 1 through 9. So that means it's going to be formed of the null set and all the single ones. There's a lot of, and all the double ones. There's a bunch of those, and all the triple ones, and there's a bunch of those. So there's like 2 to the 9. There's lots of elements in the power set, but you're looking at the power set of the set right here. Okay, so A says for every A, for every set in that universal set, the magnitude of A is not going to equal to the magnitude of the complement of A. So which is true? Okay, so let's look at all the different. Okay, so I think maybe rename this. Okay, so maybe A is not a good name for our original set. Maybe we can call this B. Okay. So A refers to a set that's in the power set. Okay, so A could be the null set, or A could be set that's just 1 or 2, or A could be the set 1, 2, and so on. It could be any element of the power set of my original set. Okay, so this is saying, is the cardinality of A, are there any sets in the power sets where the cardinality of A is going to be equal to the cardinality of the complement of A? Okay, so if I look at the different types of sets in the power set, so if I, for example, if I have the null set, so if A is the null set, then the complement of the null set is going to be the set that has all the elements. They definitely don't have the same cardinality, because this has a cardinality of 0, this has a cardinality of 9. All right, now let's look at, what if I look at the sets that they have just one element in them? And I know there's like 9 of them. But the complement of this one is going to be everything else. All right, so this has a cardinality of 1, and this has a cardinality of 8. So they're not equal to each other. Okay. All right, now we have sets that have 2 elements. All right, so that's going to have a cardinality of 2. And this is going to have a cardinality of 7, right? Because there's like 9 elements in the original set. Okay, so this is kind of what you're looking at. So are there sets in there that where they're going to be evenly spread? They're going to be the same number in the set A and the same number in the complement of the set. Okay. And it looks like the answer is no, because I have an odd number of elements in my set. Okay. Right. So my original set is 1 through 9. So there's like 9 elements in here. So there's no way that I can split them up, some in set A and sort of the opposite number in the complement of A, so they're evenly spread, because there's always going to be an odd number. So there's going to be an even number in one set and an odd number in another. So they're never going to have the same number of elements. Okay. Does that make sense for part A? All right. Part B. Oh, okay. Yeah, the universe is the power set, but when it says A, so this A right here, this is a subset of the power set. So A could be any of the sets that are in the power set. So yeah, and again, sort of for when it's B here also, like both A and B, again, this B right here is not a good name. So C is the original set. So yeah, with A and B are subsets of the power set. So they refer to sets that are inside the power set. Okay, so B right here says that there exists an A and there exists a B. So such that the cardinality of A is 5 and the cardinality of B is 5. And A intersect with B is the null set. So are there any sets in the power set they are of size 5, but they don't share any elements. Okay, and I would say this is false, right? Because if they both have 5 elements in them, they have to share elements. The only way that they can't share elements is if they are less, like 4. Right, if one set is 4 and the other one set is 5, then it's going to be like a partition that you can put 1 through 4 in one and 5 through 9 in the other. But if they're both of size 5, then they have to share one element. Okay. And C says for every A and every B in U, so for every single subset in the power set, A minus B is BC minus AC. So if you subtract A minus B, so if you look at what's in A but not in B, then this is going to be the same as what's in the complement of B and not in A. It might be worthwhile drawing like a Venn diagram for this and see how they compare. And sort of maybe a proof by Venn diagram would work well in that case. All right, I'm glad that it helped. All right, guys, if you're still around, just let me know if you have any questions.